Welcome back to the lab and to the series of anatomy lectures that we've been delivering for you. This week we're looking at the spine and specifically the structure and the osteology of the spine. So the human spine has a very specific design and is basically built for upright posture and bipedal stride. The comparison that you can see on screen is between a chimp spine and the human spine, although they're not to scale. You can see that the curvature of the chimp spine is very different to that of the human spine. In fact, the shape of the human spine is shared across many genres, and this picture very quickly shows you that actually chimps are our cousins and not necessarily where we've evolved from, although if we go back far enough, there's definitely some common ancestry there. So you'll probably be quite familiar with this image of the evolution of man. And it's not entirely accurate. There are definite links that go, like we've just demonstrated, that go back a very long time. But the human, or the Homo sapiens as we are now, is actually one of a long and diverse group of cousins that existed actually for a very long time at the same time on the planet. So some of these you'll be familiar with. The Neanderthal man and the Denisovans are probably two of the most written about because we have fairly good specimens to record and research from. But this is, so the addition of the chimp at the beginning of this is not actually probably quite as accurate as we think. If we look at the chimp, they are yes, they are related to us. Yes, we share nearly 99% of our genome with them. So we are very, very similar in many ways, but the chimp has evolved as a cousin. So the chimp has evolved as in their own line. We have evolved as bipeds. So we stand on 2 feet. In fact, we probably started in the trees as brachiating primates. So we were arboreal creatures that lived in the trees. And we eventually sort of took to the ground, perhaps as the forests shrank and the savanna plains increased. It became increasingly necessary for us to negotiate that kind of environment. And if we look at another part of the ape family, specifically the gibbons, we can actually see that they operate in a not dissimilar way, and in fact their spines are slightly different to the chimp spines and possibly closer to our own. So you might say that in fact we were born to run, and when we looked at the foot and ankle in previous lectures, we've examined that unique design of the human foot and the mobile adapter that it operates as. So let us jump into complete anatomy again, and we'll look in more detail at the vertebral column. Vertebral column is made up of 33 individual segments. These are stacked vertebrae which operate as a one unit. They articulate between each other, but there is only a small amount of articulation at each joint. So this contributes to the stability and the protection of the spinal cord. But overall, over the whole unit, it actually allows for great flexibility. And there's greater and lesser flexibility in each section, as we'll sort of see as we look at the characteristics of each of the vertebrae from each of the sections. So cervical vertebra, there is a unique feature here in that there is a foramen which is running up the middle that you can see there, where the vertebral artery lies. The thoracic vertebra in the middle, of which there are 12. The lumbar vertebra at the bottom, you can now start to see that there's an increasing size. So we go back up to the cervical vertebra. They're quite small, they're quite narrow. They don't need to carry an awful lot of weight. We've got a hefty head, but it's sufficiently supported. The thoracic is starting to get a little bit bigger, and certainly as it gets towards the bottom of the spine, they're starting to thicken up. The lumbar are very solid, chunky units which support our whole body weight. And then at the bottom, we've got 5 fused sacral vertebrae, which can be seen there, and the 4 coccygeal vertebrae, which again fuse together. The vertebral column is split into curves, and these are primarily there to give us a little bit of shock absorption and contribute to the biomechanics of the spine as a whole. The primary curves are the kyphotic curves, and they are the thoracic, sacral, and coccygeal curves. We talk about kyphosis or a kyphotic curve. Sometimes that's misconstrued as a sort of negative thing, a pathology, but in fact, kyphosis is normal. It's when kyphosis becomes a problem that it develops into a pathology where a spine is over-kyphotic or over-lordotic. And that leads us on to the secondary curve, which is the cervical and the lumbar curves, which you can see curve the other way. Cervical curve develops as the infant learns to hold its head upright, the lumbar as a child learns to walk. And so as weight bearing starts to increase and the natural biomechanics of the body take over, then we slowly adapt. Much as we spoke about the biceps, there is no groove there originally at birth. That bicipital groove develops as load is put through it. Similarly, the curves develop as we develop. Looking a little bit more closely at the cervical vertebra, we start at the foramen magnum at the top. This essentially is the big hole, foramen hole, magnum big. And if you compare this with a chimp, that's more posterior, and ours is very much underneath the skull, and that contributes to that upright bipedal posture supported by the ligaments of the spine. The first two vertebrae are slightly different. The C1, the atlas, lacks the spinous process and a vertebral body. There's the transverse process at the side. All of the vertebrae to some degree have a transverse process, which becomes more prominent as we move down the spine. And this is a common attachment for muscles and ligaments. We've got the dens there, which is a remnant of a vertebral body, but actually contributes now to the stability of those first two units, right at the top where the spinal cord is leaving the brain. C2, which is the axis, so we've got atlas and axis, which are the first two. Then we move through C3, C4, C5 and C6, which are fairly comparable. You'll notice that there's a bifid spine, slightly different shape to the spinous process. And then we have C7, which is very prominent and is very easily palpable at the back of your neck. In the centre there, you can see the vertebral canal, or the central vertebral foramen where the spinal cord is coming. So let's just identify a couple of joints. We've got the atlantoaxial joint, and above it the atlanto-occipital joint. So this is where the skull pivots and a lot of rotation occurs. So these two vertebrae are uniquely designed, a slightly different design, to allow the pivot and swing of the skull. Also highlight the transverse foramen where the vertebral artery lies. When it comes to some of the manoeuvres that may be completed as part of physiotherapy and rehabilitation therapy, manual therapy techniques, a lot of care is taken to make sure that this vertebral artery is not compromised. So a typical cervical vertebra, you can see there at the top there's an articulating facet. So that's the superior facet. If there's a superior facet, there'll be an inferior facet. All of the spine is assembled in a similar way. All of the vertebral segments are assembled in a similar way. We have a pedicle, a spinous process, which in the case of the cervical vertebra is bifid. That is, it has two sort of sections to it. We have a lamina, which is the section between the spinous process and the transverse process. We have the vertebral body, which again increases in size as we go further down the spine. The transverse foramen, where the vertebral artery sits, and the vertebral foramen. Now this forms the vertebral arch, and it changes shape as we move through the spine, because at the top of the spine we've got the brainstem becoming spinal cord, and as we move through the structure of the spine, we've got the spinal cord itself, which is ending around about T12, L1, where we have the conus, and below that we have the cauda equina, which is Latin for horse's tail, which is where a lot of the nerves have spread out and branch out towards the end. The atlas, like I said before, has a unique design. and just is a little bit of a different shape. We won't cover it in too much detail in this lecture, but if we just identify the foramen, you'll see that it is much bigger, because this is where the brainstem lies. Similarly, the axis, again, is important that we just perhaps identify that foramen. Again, quite big, getting slightly smaller as the brainstem is turning into spinal cord. We're now sort of narrowing up. Looking now at the thoracic vertebra, the vertebral body is starting to get larger. The vertebral foramen is starting to get a little bit smaller and more cord-shaped. So the spinal cord now is very much a cord. We've left the brainstem behind long ago, and now we're sort of descending down through the thoracic vertebra to the end of the spinal cord. Superior articulating facet at the top. Now these are synovial joints, and this is important to therapists in treating the spine, that they appreciate that these joints can be, they are synovial joints, therefore they have capsules and ligaments. They can get swollen, they can get inflamed, and often that needs treating and can be a cause of back pain. Here's the transverse costal facet, so being the thoracic vertebra, this is where the ribs come round, and the ribs come and knuckle in to the vertebra at this point. The transverse process out to the side starts to become more prominent because there are more muscle attachments. And the spinous process, you can see there, is slightly different shape, it actually drops down. So what we find is that the spinous process of the level is as we move down to that process to where it's palpable, it's actually level with the vertebral body of the segment below. Inferior articulating facet. So if we go back to this superior facet, you'll notice that they're facing in different directions. And this is important when you understand the way the vertebrae is stacked, and it helps you understand exactly how the spine operates in its rotation, the way these joints open and close, and as you flex and extend, as you laterally flex, and as you rotate. And rotation is important because as you rotate one way, then the facet joints will close, and rotate the other way, the facet joints will open. And we'll look at that in greater detail in the face-to-face sessions. The superior articulated facet has a process it's attached to, and then as we sit here, this is where the vertebral bodies articulate, and these are called the demifacets. Again, we have the pedicle and we have the lamina. Just in the thoracic spine, they're just a slightly different shape, but they exist nevertheless. Moving to the lumbar vertebra, we can now see that the vertebral body is much bigger. The vertebral foramen has actually started to widen again, because at this point the spinal cord has come to an end of the conus. The conus is sitting more or less at this point at L1, T12 to L1, and the vertebral foramen needs to now enlarge because of the cauda equina. The articulating facets are now in a slightly different direction because we have no ribs anymore, and there's a slightly more flexibility at this point. We have a superior articulating facet facing one direction and the inferior articulating facet in another direction. The transverse process is very prominent and is an important attachment point for muscles such as the quadratus lumborum. The erector spinae sit in the gap, and the psoas muscle, psoas muscle is coming through from the transverse process down to the lesser trochanter. The lamina is very prominent and obvious. The pedicle at this point is very obvious. There's definitely more shape to it now. They're thicker and larger. And the notches there which form the foramen at the side where the spinal nerves arise, they've become more prominent because the cauda equina has larger branches of nerves. They form the sacrum and the lumbar plexus. So again, they need more space for the nerves to get out. Finally, a quick look at the sacrum and the coccyx. Now these have been fused together through our evolution. The sacrum we've looked at before when we looked at the pelvis and the hip in a little bit of detail, but you can see there that there is a very large articulated surface. the sacroiliac joint. The anterior sacral foramina is where you'll see the sacral nerves arise and form the sacral plexus. Just very quickly, we'll run through S1, S2, S3, S4, and S5. Sacral canal is there. We've got the cauda equina sort of finishing its journey now as it reaches the bottom, and the final spinal nerves are exiting. Posterior view, and the anterior view, and then we're finishing off with the first coccygeal, second, third, and fourth. In the face-to-face sessions, we'll go through the structure of the spine in a little bit more detail. We'll examine exactly how the spine rotates and flexes and extends, and laterally flexes and extends, how the vertebral discs contribute to the shock absorption and the stability of the spine, and we will look in more detail at how we assess the spine. In the next video, we'll be looking at the musculature and some of the ligament structures in a little bit more detail, so we can appreciate exactly how the spine moves and how we have this natural passive stability to the whole unit, which contributes again to our ability to stand on 2 feet in an upright posture. Thank you for listening, and we'll see you back in the lab in the next video.